Hello 20-1 students. So today we're looking at lesson 7.4, looking at reciprocal linear functions. Now today's set of notes is a little bit longer, so I might kind of test out and see where we get to. There's a chance I'll divide this lesson into two parts. There's definitely time in the timeline for that to happen, so we'll just kind of see how the lesson goes. So just remember that a little bit of information about reciprocals. So remember that the product of a number and its reciprocal is always equal to 1. So a reciprocal is like the flipped version of the fraction of the number. So for example, if we had, let's say 3 as a whole number, then we would write it as a fraction as 3 over 1. And what we're saying here is that the product of that number and its reciprocal, so product always means multiplying. So if we multiply this by the reciprocal of its number, which is this fraction flipped, which would be 1 over 3, and it's saying that's always equal to 1. So remember, when we multiply a fraction, we multiply straight across. So 3 times 1 is 3, 1 times 3 is 3, 3 divided by 3 is 1. So we can see proof for that statement there. So for any number that's not 0 basically, which we can represent with the variable a, the reciprocal of that number, which we're representing with a, is 1 over that value, and the reciprocal of 1 over that value is the number, of course. So for a function, if we're moving into things that are a little bit more complicated, its reciprocal is going to be 1 over that function, as long as the function does not equal 0, right? Because that would be undefined. We can't have 0 as a denominator. So we're going to do a little bit of investigation with the idea of reciprocals before we get into kind of some more in-depth examples. So we want to basically think about how functions and their reciprocals are related. So in these tables, we're given a bunch of values for x, and then we're given the values of y for the function of x, right? So basically, if we have a function where all the values of y on the graph are equal to the values of x, we're solving for the values of y. So of course, they're going to be the same as x. Now, if we have a function y where it is equal to, y is equal to the value of the reciprocal of x, so 1 over x, we want to determine what the values of y will be in that graph. So of course, it's just going to be the reciprocal of our x value. So if we had negative 10 as x, we would have negative 1 over 10 for y. If we have negative 5 for x, we're going to have negative 1/5. Negative 2 would be negative 1/2. Negative 1 would be negative 1 over 1, which is just negative 1. Negative 1/2, if we flip that, is negative 2 over 1, which is just negative 2. Same thing for this. Negative 5 over 1 is the reciprocal, so it's just negative 5. And negative 10 over 1 is negative 10. Okay. Then if we look at this second set, we have another set of values that we can look at here. So if x is equal to 0 on the graph, y equals x, y is 0 as well. The reciprocal of that would be 1 over 0. And so we see that that is going to be undefined, right? So we're not going to see that value on the graph. Then going through the remaining reciprocals here, we have 1 over 10. The reciprocal of that is going to be, if we flip this back over, 10 over 1, which is just 10. Same thing here, reciprocal is 5 over 1, which is 5, 2 over 1, which is 2, 1 over 1, right? Because this written as a fraction would be 1 over 1. If we flip it, it's the same thing, so regardless, it's 1. For this one, it would be 2 over 1, and the reciprocal of that would be 1/2, 1 over 2. Okay? So we can basically see that for the reciprocal of any given function, so the last column versus the middle column, basically the thing that is going to change, our x values remain the same for both, but the correlated y values in the original graph and the reciprocal are just going to be the inverse values of each other, right? So it's always going to be the reciprocal for both graphs. So we want to try and think about answering some questions about these graphs. How did we find the values for the reciprocal function? So in order to find those values, we basically always took the values of the original function and divided them by 1. So essentially that would be that we did 1 divided by the function. Okay, or the original function. What is unique about the reciprocals of -1 and 1? So if we look here, when we had -1, we see that the reciprocal is still -1. And when we had +1, the reciprocal is, of course, +1 still. So the unique thing about those two is that if we look through each one of these columns, we see that the only place where our values are the same in both columns for the original and the reciprocal is when the value is equal to plus or minus 1. So basically, they are the same as the original is what's unique. Same as original. And we're going to actually learn that these points have a special name for them because they're the same on both graphs. Next one, why is the reciprocal of 0 undefined? So we've talked about this a little bit because you can't divide by 0. Can't divide by 0. Okay. In the next part, it says graph y equals x and y equals 1 over x on your graphing calculator and sketch in the grid below. So basically, what we want to do is go to our graphing calculator and put in our two different values for y. So for our first one, we just wanted to put in y equals x, so we can just put that in, and then we want the reciprocal, which is going to be 1 divided by x. And then if we go to our graph, here we can see, so this is y equals x, right? Of course, we're going to see a linear function there because it's just going to have every value of y equal to x. In red, we see our reciprocal. If you guys are ever not sure how to identify which one of your graphs is which, you can see that the color is listed here. Of course, that's for this color version, so I'm actually not sure anymore for the regular TIs how you could tell. Although they will always graph them in order too, so when you go to the graph and you see the first time and you see the lines coming up, the first one will always be the first graph you entered, and the second one will always be the second, and so on. Okay, so and here we see our reciprocal function looking quite a bit different. So basically what we have with our y equals x, if you were to go in and trace the different values for our linear value, basically y is going to be equal to x. So it would be like -1 and -1, -2, -2, -3, -3, -4, -4, +1, +2, +3. So that's going to be our linear function. Let's see if I have that mostly lined up there. So that is y equals x. Now for our inverse function, we see something really different, right? We see that this red line along the x-axis, you can see that it looks like it's getting pretty close to 0. What you might not be able to tell is that it's always going to approach 0, but never actually get to 0. And then same thing, it cuts off here actually, but basically this would extend down and do the same thing over here. So essentially what it would do is approach 0 on both the y and the x-axis, but never quite touch it. So essentially it's going to be kind of like, and I'm not going to measure out exactly where that would be, but okay. So, and then the second one goes up here. and then kind of does the same thing going down like this. So if I were to maybe quickly run a highlighter over this one so we can differentiate it. So that would be our y equals 1 over x is going to be the pink graph there. So if we look at our table of values, I'm just going to pull up the filled in version that I had so we can compare these two things. If we look at our values on these charts, can we make sense of why this graph looks the way it does? So first of all, sorry, it's hard to get these both on screen. Okay, so let's look at this one first. So in this case, we had a lot of negative x values, right? All of our values for x were negative. And when we look at the reciprocal function, what do we see? So when we have these larger versions, values of x, we have a much smaller, the reciprocal is going to be 1 over 10, which is a very small fraction. And then as we increase our values for x, so getting closer to 0, we see that our fractions become larger, going to negative a fifth, negative a half, negative 1, negative 2 for our y values, and then negative 5, negative 10. So what we're seeing here is that along the x-axis for these high negative x values, our y value is going to be the reciprocal, which is going to be increasingly small fractions. But as long as we have a value for x, we can never equal to 0. We're just going to have a smaller and smaller fraction, right? So as our values for x get higher, we're going to have like 1 over 20, 1 over 30, 1 over 40. So we're always approaching 0, but never quite getting there. And then as our values for x get smaller and smaller, so we're going down into like the halves, the quarters, the eighths, whatever it might be, our fraction here, again, is going to be approaching 0, but it's never going to reach it. And our values for y are getting increasingly large, right? So we're going to see this graph continue down into higher and higher y values. The exact same thing happens over here with our positive x values. So we have smaller fractions are going to be larger x values. So when we're really close to 0, we have really high values of y. And then as our values of x get larger, so we're going to like 1 and 2, we're going to start seeing our values for y get lower and lower, and we're going to start seeing those fractions go down, which is why we're approaching 0 on this side. And so the last thing I want to point out here is, how did we end up with this undefined component, and what does that mean? Well, basically, 0 is undefined because neither one of these portions of the graph, the reciprocal graphs, can ever touch 0. So it's like a non-permissible value, and that's because it is an undefined number for the reciprocal. Okay, so hopefully that helps you to understand the idea of these reciprocal graphs a little bit better. We're going to get into some more kind of graphing details now about this. So looking at the graph's domain and range. For our x values, for y equals x, we had that linear function. What would we say the domain is? Well, there's no restrictions on either the domain or the range, right? So I could have drawn this a little bit better by including arrows, because as long as we have x values and y values, it's going to continue on indefinitely. So for our domain, we would say x is equal to all real numbers. And for our range, same thing, right? Y is equal to all real numbers. What about for our reciprocal function? So in this case, we see x could go on kind of infinitely in the negative direction or infinitely in the positive direction. The only restriction is that they can never get to this 0 point on the x-axis. So when we write that as a domain, we're just going to say x has to be greater than 0 and x equals all real numbers. The other way, actually, you know what? We shouldn't say greater than, because it could be, x can be a negative value. So what we want to say instead there is x just cannot equal 0. We could also say greater than or less than, but that just kind of becomes cumbersome to write out. What about our y values? Well, again, we had the same situation, right, where the y can never quite approach the zero, like this graph will never approach the x-axis, which means it'll never approach 0 for y. So basically the same set of restrictions is what we find for the range. So y cannot equal 0, but for the rest, other than that restriction, y can equal all real numbers. Okay, another thing we need to be able to describe with these types of graphs is something called the end behavior. So the end behavior of a graph is basically just how is the graph behaving as it approaches positive or negative infinity. So with the y equals x, we just saw that linear function kind of going into infinity. So how we describe the end behavior is how the different x and y components are behaving relative to each other. So as x increases, we could say, you could also say as x decreases. As x increases, y increases. Okay, and then also, like I just mentioned, as x decreases, y decreases, right? So those two things are just happening exactly the same because they are equal to each other. For the reciprocal, what would we say as x is increasing? So we would say as x increases, right? So as our values for x are getting higher, what is happening to our values for y? They are approaching 0. Okay, so we're going from high y values and then we'll go down to a half, a fifth, a tenth, and so they'll approach 0. So as x increases, actually we could make that a little bit more formal. Let's say as x increases from, I was going to say from 0, but oh yeah, well I guess, no, because x values wouldn't be 0. So let's just say as x increases, maybe let's say in the positive direction. Just to be really specific, as x increases in the positive direction, y gets close to 0. And then we would say as x decreases in the negative direction, what is happening with y direction? So again, as our negative values became larger for x, so we're going from like 1, 2, 5, our y values are getting slower. So we would again say y gets close to 0. Or y approaches 0 is another way to say that. So when you're writing out end behavior and things like this, there's obviously multiple ways to write it. Just make sure that you're giving the proper like general idea of what's going on. But I don't want you guys to fixate on like there only being one correct way to write those. As long as you're giving the general trend, you should be okay. Last one, are there any invariant points? So if you remember, I mentioned that we're going to learn a special name for 2 special points. So what were our unique points on this chart? The unique points were the ones where the value of x and the value of y in the original graph and the final graph were all the same. And those 2 points are always -1 and +1. And so actually what we can kind of do is get rid of this line that divides these two apart because invariant points apply to both of the graph. That's the whole point of them. So an invariant point is a point that's the same on both y equals x and y equals 1 over x. And so those points would be x equals -1, y equals -1, or x equals +1, y equals 1. And this applies to both of them, which is why they're invariant points. So we can just kind of fill it in without that separation between the two. All right, so a couple of pieces of vocab before we look at some examples of working with graphing reciprocal functions. If we have something called an asymptote, which is a line whose distance from a given curve approaches 0. So in the graph that we drew, the asymptote, if we think about what that definition was, it's a line whose distance from a curve approaches 0. So in this case, that was actually the y-axis was an asymptote, or we could say x equals 0 was the asymptote, because it's basically a line, and this given curve is approaching it in like an increasing distance that approaches 0 but never quite gets there. So the next definition here is a vertical asymptote, which is basically for reciprocal functions. This isn't always going to be like our y-axis here. It could be any value of x, and it's always going to occur at the non-permissible values of the function for the reciprocal function. So any values that would make the denominator of the reciprocal function equal to 0. So that could be like x, like if your non-permissible value was 2, for example, then that would mean you would have this same kind of a setup with these graphs, but they would be shifted over to the right, and neither one of them would quite be able to touch the line of x equals 2. So if you were to graph x equals 2, you would have a line there, and neither one of these would approach there. So that's our vertical asymptote. If you were asked to list the vertical asymptote or the asymptote, you always just write it as x equals whatever that non-permissible value is. Horizontal asymptote is kind of the same thing, but going horizontally, of course, and so that would be like, in this case, neither one of these could approach the x-axis, right? So that would be y equals 0, and so that's how we would express a horizontal asymptote as well. Generally, with our functions that we're going to be looking at, we're always working with listing the vertical asymptote, so x is equal to a value. So let's give an example a try here. We have the function x plus 5, and we want to graph the reciprocal of the linear function. So the first thing we want to do is state the zeros. So the zeros are the values where the function is equal to 0, so basically where y is equal to 0. So for the original function, that's going to be 0 is equal to x plus 5, and then rearranging that, we would, to solve for x, we would subtract 5 from both sides, and that's going to leave us with, I don't have a room down there, so I'll put it as x is equal to -5. Okay, so that's our 0. We could write that as a coordinate too, where we would have -5 and the y value would be 0. Then we want to write the reciprocal function. So the reciprocal function is just 1 over our original function. So we had x plus 5 as our original function, and the reciprocal is going to be 1 over that. State the non-permissible values corresponding to the rational expression. So which values would make the denominator of this 0? Well, if we had -5 is the only possibility, right? Because -5 plus 5 would be 0. So we would say x cannot equal -5. Then it says state the vertical asymptote. So like we mentioned, vertical asymptotes are always going to be your non-permissible values for the reciprocal function. So our our vertical asymptote, remember we write it just as x equals a. So it's going to be the same as this, except for instead of saying cannot equal, it's x does equal -5. Okay, now if we put that into a graph on our calculator a second, let's see what that looks like. So let's go to y equals, and we could clear that out. Y equals 1 divided by x plus 5. And if we go to our graph, so basically, if we look at what's happening here, if we were to trace these values, so let's put a trace in here. we can see that we have x is increasing 1.8, 1.9, negative 2, negative 3, negative 4, and then we have negative 5, and see how it jumps to no value for the y. And what it's actually going to do is if you keep tracing, it'll jump across to the other one, and we see that starts at negative 5.15. So this, I don't know why the graphing calculator exactly does this, where it doesn't graph the full function like extending into infinity. But basically what that's showing you is that negative 5 is going to be your non-permissible value because it jumps from one component of the function to the other component, right? And they're both on increasing values or decreasing values of negative 5. Okay. All right, so we're at 25 minutes, so I think I am going to end up breaking this into 2 different parts. And so you guys have a chance to try this one here, the your turn, and you can check the filled in notes for the final for the worked solution for that one, so you can check your work. And then I'll actually I'll modify these notes and give you guys a textbook assignment, so it'll be listed at the bottom of this page. So just make sure you check for that textbook assignment in your notes and make sure that you complete it for practice, and I will see you in the next lesson.